Welcome, my friend. Tonight, I'll take you through the remarkable life and theories of Stephen Hawking, from black holes that shine to the very shape of the universe itself. This video is designed not just to teach you, but to help you drift into rest. If you're visiting this channel for the first time, know that every story here is told slowly and calmly, so you can both learn and fall asleep at the same time. Let's begin. Chapter 1. The Young Rebel, from General Relativity to Black Holes. When we speak about Stephen Hawking, it is tempting to begin with the myth, the brilliant young man struck by illness, who nevertheless rose to become one of the most celebrated scientists of the 20th century. But if we want to understand the roots of his greatest theories, we have to start with the intellectual landscape into which he entered, and the way he used general relativity, a theory that was already half a century old when he began his work, as the foundation for his radical insights about the universe and black holes. Einstein's General Relativity, published in 1915, describes gravity not as a force but as the curvature of spacetime. Mass and energy tell spacetime how to curve, and spacetime tells mass how to move. This framework explained the orbit of Mercury, predicted the bending of light by the sun, and laid the foundations for modern cosmology. But by the time Hawking was born in 1942, relativity had both triumphs and limitations. On one hand, it had predicted phenomena like gravitational redshift and was being used to model expanding universes. On the other hand, its equations were notoriously difficult to solve, and many physicists preferred the quantum field theories that were flourishing in mid-century particle physics. Relativity seemed remote, abstract, and mathematically forbidding, and cosmology was not considered a fashionable field of research. Hawking entered Cambridge in the early 1960s, already showing signs of the motor neuron disease that would later confine him to a wheelchair. Despite his illness, he carried a rebellious spirit into his studies. He was impatient with conventional thinking and sought to use general relativity in ways that others had overlooked. His PhD supervisor was Dennis Sciama, a leading figure who encouraged his students to tackle fundamental questions in cosmology rather than narrow technical problems. Under Sciama's guidance, Hawking gravitated toward the study of singularities and the ultimate fate of collapsing stars. At that time, the understanding of black holes was incomplete. Karl Schwarzschild had found an exact solution to Einstein's equations in 1916, describing a spherically symmetric mass. Yet for decades, this solution was regarded as a mathematical curiosity rather than a physical object. It seemed absurd that real stars could collapse into an infinitely dense point. Only in the 1960s did the work of John Wheeler and others begin to establish black holes as plausible astrophysical entities. Wheeler coined the term black hole in 1967, and the field began to grow rapidly. Hawking was entering this area just as it transformed from fringe speculation into a serious branch of physics. His early work focused on applying general relativity to questions of cosmic origin. The prevailing cosmological model was the Big Bang, but some alternatives, such as the steady-state theory, still had defenders. The central issue was whether singularities, points where density and curvature become infinite, were unavoidable consequences of Einstein's equations or merely artifacts of idealized assumptions. Roger Penrose, a mathematician at Oxford, had recently proved that singularities were inevitable in the collapse of massive stars, provided certain reasonable conditions held. This was a breakthrough, because it suggested that singularities were not mathematical accidents, but physical predictions of general relativity. Hawking was inspired by Penrose's methods, which used global techniques in differential geometry rather than local coordinate systems. These techniques allowed physicists to make general statements about space-time without solving the equations in detail. Hawking realized he could extend Penrose's approach to the entire universe. If singularities are unavoidable inside black holes, might they also be unavoidable in the past history of the universe? Working through the mathematics, Hawking demonstrated that under very general conditions, an expanding universe must have originated in a singularity. In other words, the Big Bang was not just a speculative story, but a rigorous implication of Einstein's equations. This was a daring conclusion, especially for a young researcher. At the time, many physicists preferred to imagine that the Big Bang could be smoothed out by some mechanism that avoided infinite density. Hawking, however, embraced the singularity as a clue that general relativity was pointing beyond itself. Singularities marked the limits of the classical theory, where quantum effects must take over. He had already set the tone for his career, pushing general relativity as far as it could go, showing its surprising consequences, and then using those consequences to highlight the need for new physics. Hawking's rebellious streak was not only intellectual, but also personal. Despite his diagnosis of amyotrophic lateral sclerosis, doctors initially gave him only a few years to live. Rather than discouraging him, this prognosis seemed to focus his energy. He married Jane Wilde in 1965, just as his health was deteriorating, and threw himself into his research with extraordinary intensity. Friends and colleagues remember his mischievous humor, his refusal to dwell on limitations, and his competitiveness. He wanted to challenge the giants of physics, not revere them. General relativity provided the perfect arena for such challenges. While quantum theory was crowded with Nobel-level researchers, relativity and cosmology were fields where a bold young thinker could make a mark. By the late 1960s, Hawking had already become a central figure, collaborating with Penrose and others, and driving forward the understanding of space-time singularities. His work helped establish that black holes were not just mathematical constructs, but unavoidable features of gravitational collapse, and that the universe itself had sprung from a singular state. The path from general relativity to black holes was therefore both scientific and personal for Hawking. He took a theory created by Einstein, extended by Penrose, and pushed it further, showing that the cosmos itself carried the imprint of these ideas. In doing so, he helped transform black holes from exotic possibilities into central players in astrophysics. Later, he would go further, showing that black holes emit radiation, evaporate, and raise paradoxes about information. But even in his earliest work, we see the outlines of his style: clarity about the rules of general relativity, courage to follow them to extreme conclusions, and a willingness to embrace paradox rather than avoid it. Scientifically, this first phase of Hawking's career illustrates how a single theory, general relativity, can yield profound consequences when interpreted creatively. Relativity is deterministic, but its solutions can lead to breakdowns where predictability fails, such as singularities. Hawking recognized that these breakdowns are not failures of mathematics but signals of deeper layers of physics. His insistence on taking singularities seriously laid the groundwork for later explorations of quantum gravity. The implications extend far beyond technical results. If singularities are inevitable, then our universe had an origin in which the known laws of physics ceased to apply. This forces us to ask whether the universe had a cause, whether time itself began, and whether physical explanation can ever be complete. Hawking was not the first to ponder such questions, but his mathematical proofs gave them a new authority. He showed that the mysteries of origin are not philosophical ornaments but scientific necessities. Looking back, it is striking how the trajectory of Hawking's own life echoed the themes of his science. His body was collapsing, but his mind pursued the structure of collapsing stars. He was given a finite prognosis, but his work dealt with the finitude of time itself. He took a theory developed by Einstein half a century earlier and showed that it still contained secrets, much as his own life, though constrained by illness, contained an astonishing productivity. And so Hawking began his career as the young rebel of cosmology, turning general relativity from a beautiful theory into a tool for unveiling the darkest and most mysterious aspects of the universe. His early work set the stage for everything that followed: the radiation, the paradoxes, the no-boundary proposal. It showed that physics was not done with the great questions, that even in a world of particle colliders and quantum electrodynamics, there was still room to ask about beginnings and infinities. Perhaps this is why Hawking's work resonates so widely. It reminds us that the universe is not tidy, that the very equations we use to describe it can point us to their own limits, and that those limits are where discovery begins. In confronting singularities, Hawking did not shy away from the abyss but leaned into it, insisting that science must grapple with the deepest unknowns. At the existential level, there is something both humbling and inspiring in this story. If the universe began in a singularity, then everything we are, our stars, our planets, our lives, emerged from a point where the laws of physics themselves falter. Out of that opacity came the clarity of existence. Hawking's own life mirrored this lesson. Out of physical limits came intellectual expansion. Out of struggle came insight. It suggests that even when the structures around us collapse, new possibilities can emerge. As you let these thoughts settle, imagine the calm persistence of the cosmos itself. The stars wheel slowly in their courses, black holes bend light silently in the dark, and space-time continues its patient unfolding. Hawking's theories invite us to marvel, but also to rest, knowing that we are part of a universe whose mysteries stretch far beyond the concerns of a single day. Whatever challenges have filled your hours, you can let them fade now, as the quiet immensity of the universe surrounds you. Let the questions linger in the background, but allow your mind to drift, calm and unburdened, into rest. Chapter 2. The Hawking-Penrose Singularity Theorems. The early years of modern cosmology were filled with speculation, competing models, and vigorous debate. In the decades after Einstein formulated general relativity, solutions to his equations suggested strange possibilities: universes that expand or contract, stars that collapse beyond recognition, and regions where the known laws of physics break down. Yet for much of the mid-20th century, many physicists believed that these extreme consequences were artifacts of idealized assumptions rather than robust predictions. Surely nature would find a way to avoid infinities. It was in this intellectual climate that Roger Penrose and Stephen Hawking made their mark, proving with mathematical precision that singularities are not optional quirks, but unavoidable features of spacetime under quite general conditions. Their singularity theorems changed the way physicists thought about the universe's origin, the interior of black holes, and the ultimate reach of Einstein's theory. A singularity in the context of general relativity is a place where curvature becomes infinite and where geodesics, the natural paths through space-time, come to an end. To speak more plainly, it is where the framework of relativity itself ceases to provide predictions. This is not merely a point of high density or pressure. It is a breakdown of the theory's descriptive power. For decades, physicists hoped these singularities were only consequences of assuming perfect symmetry, like a star collapsing in a perfectly spherical manner. Real matter distributions are messy and uneven, so perhaps nature would smooth over the infinities. The Hawking-Penrose theorems demonstrated that this hope was misplaced. Penrose struck the first blow in 1965 when he published a paper showing that under very reasonable conditions, the gravitational collapse of a sufficiently massive star would inevitably lead to a singularity. He introduced the concept of trapped surfaces, regions where light rays are forced to converge. Once such a surface forms, general relativity dictates that the collapse cannot be halted. Penrose's proof did not rely on symmetry or on special properties of matter. It showed that collapse to a singularity is the generic outcome of Einstein's equations. This work earned Penrose wide recognition and set the stage for Hawking's entry into the field. Hawking, then a young researcher, saw that Penrose's methods could be extended beyond stellar collapse to the entire cosmos. If general relativity was taken seriously, then the same mathematics that proved singularities inside black holes could also prove a singularity at the origin of the universe. Working through the details, Hawking showed that under the assumption of general relativity and the presence of matter satisfying certain energy conditions, an expanding universe must have begun in a singularity. This was a striking result. It meant that the Big Bang was not just a convenient story, but a necessary consequence of the theory. Together, Hawking and Penrose developed the singularity theorems that now bear their names. These theorems use techniques of global differential geometry to make statements about entire spacetimes rather than local patches. Instead of solving Einstein's equations for particular cases, they considered the causal structure of spacetime and the behavior of light cones. By analyzing how geodesics can or cannot be extended, they proved that under quite broad assumptions, spacetimes with trapped surfaces or persistent expansion inevitably contain incomplete geodesics, signatures of singularities. One of the striking aspects of these theorems is their generality. They do not require exact symmetry, nor do they demand exotic matter. They work under conditions that are entirely reasonable by the standards of classical physics. This generality forced physicists to confront singularities as genuine predictions rather than as artifacts of oversimplified models. The universe we inhabit and the stars within it are messy and dynamic. Yet the theorems show that singularities still arise. The implications were profound. In cosmology, the singularity theorems supported the Big Bang model by showing that any universe undergoing expansion, given the energy conditions, must have originated from a singular state. This was a powerful blow to the steady-state model, which posited an eternal universe with continuous creation of matter. Observational evidence, such as the discovery of the cosmic microwave background, had already tilted the balance toward the Big Bang. But Hawking's mathematical result gave it theoretical inevitability. In astrophysics, the theorems reinforced the reality of black holes. If massive stars collapse beyond a certain point, they must end in singularities. The question was no longer whether black holes existed, but how they behaved, how they interacted with their surroundings, and what role they played in galactic evolution. The singularity theorems thus turned black holes from speculative curiosities into central actors in the cosmic story. Equally important was the philosophical consequence. Singularities mark boundaries where classical general relativity ceases to function. They are not merely locations of high density, they are regions where predictability fails. If spacetime has an edge, then physical law cannot be extended beyond it. For the universe as a whole, this means that the Big Bang singularity is a point where the known laws cannot say what, if anything, preceded it. For black holes, it means that inside the event horizon, physics cannot describe the final state of collapse. In both cases, the theorems force us to acknowledge the limitations of our theories and the need for a deeper framework, most likely a theory of quantum gravity. The collaboration between Hawking and Penrose also illustrates the power of combining different perspectives. Penrose approached the problem with the tools of mathematics, bringing rigor and new techniques from geometry. Hawking, trained as a physicist, brought physical intuition and cosmological ambition. Together, they produced results that were both mathematically elegant and physically consequential. This partnership cemented Hawking's reputation as a bold thinker willing to confront the most fundamental questions. One of the subtler points of the theorems is their reliance on certain energy conditions, assumptions about the nature of matter and energy. For example, the so-called strong energy condition asserts that gravity is always attractive in classical contexts. These conditions are reasonable for normal matter, but quantum field theory has shown that they can be violated in exotic circumstances, such as with negative energy densities. This does not invalidate the theorems, but it points to the edge where quantum effects may alter the conclusions. Hawking himself later explored how quantum mechanics could modify the fate of black holes, leading to his discovery of Hawking radiation. It is worth noting that the singularity theorems do not describe what happens at a singularity. They only prove that geodesics cannot be extended, that the structure of space-time is incomplete. They tell us that there is a boundary to classical physics, but not what lies beyond it. This is why singularities are often described as signs that our theories are incomplete. They are less predictions about specific physical states than they are indicators of where our current framework breaks down. In retrospect, the impact of the Hawking-Penrose theorems can hardly be overstated. They reshaped cosmology by giving the Big Bang theoretical necessity. They reshaped astrophysics by demonstrating the inevitability of singularities in gravitational collapse. They reshaped the philosophy of physics by confronting scientists with the limits of prediction. And they reshaped Hawking's own career, setting him on a path that would lead to his most famous discoveries. For Hawking, the theorems were more than a technical triumph. They were a statement of method, push existing theories to their logical limits, no matter how uncomfortable the results. Where others might have sought to avoid infinities, Hawking embraced them as clues. This willingness to follow equations into the unknown became his hallmark. Whether studying black holes, radiation, or the structure of the cosmos, he was always guided by the conviction that the mathematics, taken seriously, would point to new truths. At the existential level, the singularity theorems remind us that the universe has edges of knowability. There are boundaries beyond which our concepts fail, places where the familiar language of space and time ceases to apply. For some, this is unsettling. For others, it is a source of wonder, a reminder that reality is not exhausted by our theories. Hawking and Penrose showed us that mystery is not a failure of science, but a necessary part of its advance. And as you reflect on these ideas, you can also let them bring you a measure of calm. The cosmos has been unfolding for billions of years, governed by laws that reach to the very edge of comprehension. Singularities remind us that we are part of something vast, intricate, and still unfinished in our understanding. As the day winds down, let your own thoughts settle like dust in the great silence of space. The questions remain, but for now, you can rest in the knowledge that wonder itself is part of the human inheritance, and tomorrow will bring new light to explore it. Chapter 3. Black Hole Thermodynamics, When Gravity Meets Entropy. The singularity theorems establish that black holes in the Big Bang were not avoidable oddities, but necessary outcomes of general relativity. Yet those theorems raised as many questions as they answered. If black holes are real, and if they contain singularities where the known laws break down, how do we describe them as physical objects? What rules govern their behavior? In the early 1970s, Stephen Hawking and his contemporaries began to realize that black holes could be understood not only as gravitational phenomena, but also as thermodynamic systems. Out of this realization was born the field of black hole thermodynamics, an unexpected union between Einstein's theory of gravity and the laws of heat and entropy. To appreciate the depth of this achievement, we need to recall what thermodynamics represents in physics. The 19th century science of heat and work, developed by figures like Carnot, Clausius, and Kelvin, gave us the concept of entropy, a measure of disorder or of the number of microscopic configurations consistent with a macroscopic state. Entropy always tends to increase in an isolated system, a principle known as the second law of thermodynamics. This law underpins our understanding of irreversibility, the arrow of time, and the tendency of energy to spread out. It is one of the most universal statements in all of science. On the other hand, general relativity seems far removed from these concerns. It describes the smooth geometry of space-time and the motion of matter under gravity. A black hole, in its simplest form, is a region where gravity is so intense that nothing, not even light, can escape. From the outside, it appears perfectly featureless. According to the no-hair theorems developed in the 1960s, a black hole is completely characterized by only three parameters: its mass, its electric charge, and its angular momentum. All other information about the matter that collapsed to form it is hidden behind the event horizon. A black hole seems to erase details and reduce complexity. It was precisely this simplicity that led physicists to wonder if black holes might obey thermodynamic laws. In 1972, Jacob Bekenstein, then a graduate student, argued that black holes must have entropy. His reasoning was straightforward but profound. Imagine throwing a cup of hot tea full of entropy into a black hole. From the outside, the entropy seems to vanish because the black hole absorbs the matter and gives back no details. If this were truly the case, the second law of thermodynamics would be violated. To preserve the universality of the second law, Bekenstein proposed that black holes themselves must carry entropy proportional to the area of their event horizons. The more mass or energy they absorb, the larger their surface area becomes and the greater their entropy. At first, Hawking was skeptical. The idea of attributing entropy to an object that appeared to be perfectly featureless seemed strange, even wrong. But his own calculations soon led him to a startling realization. In collaboration with Bardeen and Carter, Hawking helped formulate the four laws of black hole mechanics, analogues of the four laws of thermodynamics. The surface gravity of a black hole, for instance, behaved like temperature, the area of the event horizon behaved like entropy. These were suggestive parallels, but Hawking still doubted that black holes could truly radiate or have temperature in a physical sense. They seemed too perfect, too absolute. The breakthrough came when Hawking considered the interaction between quantum fields and curved spacetime. In 1974, he discovered that black holes are not entirely black, but emit radiation due to quantum effects near the horizon. Virtual particle pairs, normally confined to fleeting existence, can be separated by the horizon, with one particle escaping while the other falls in. To an external observer, the black hole appears to radiate. This phenomenon, now known as Hawking radiation, implied that black holes have a real temperature and a real entropy. What Bekenstein had proposed as a necessity became a concrete prediction. Black hole thermodynamics therefore revealed a deep and unexpected unity between three great pillars of physics: general relativity, quantum theory, and thermodynamics. The entropy of a black hole is proportional not to its volume, but to the area of its event horizon. This was an astonishing result because it suggested that information about the contents of a region of space is encoded on its boundary, a hint of the holographic principle that would later emerge in string theory. The proportionality constant is enormous. The entropy of a stellar mass black hole dwarfs the entropy of any ordinary object. In effect, black holes are the most entropic entities in the universe. The thermodynamic picture of black holes also changed the way physicists thought about the arrow of time. The area theorem, proved by Hawking before his radiation discovery, showed that the area of a black hole's event horizon never decreases in classical general relativity. This mirrored the second law of thermodynamics, in which entropy never decreases in an isolated system. Once quantum effects were included, black holes could shrink as they radiated, but their entropy remained consistent with the generalized second law, which combines ordinary entropy with black hole entropy. This marriage of laws provided reassurance that the great principles of physics were not in conflict, but it also highlighted puzzles that remain unsolved to this day. One of those puzzles is the information paradox. If black holes radiate like black bodies and eventually evaporate, what happens to the information about the matter that fell in? Does it disappear, violating the fundamental principles of quantum mechanics, or is it somehow preserved in the radiation or in subtle correlations? Hawking initially argued that information is lost, while others believed it must be conserved. The debate raged for decades and remains a central problem in theoretical physics. Black hole thermodynamics thus not only unified fields, but also exposed their tensions. It is difficult to overstate how radical these ideas were at the time. The notion that black holes could glow, that they had entropy proportional to area, and that their properties were deeply tied to thermodynamics was revolutionary. It transformed black holes from bizarre dead ends of general relativity into laboratories for fundamental physics. They became testing grounds for ideas about quantum gravity, string theory, and the very structure of space-time. What is most remarkable is how these insights grew from a simple insistence on consistency. Bekenstein refused to believe that the second law could fail, and Hawking, though initially doubtful, followed the mathematics where it led. The result was a synthesis that continues to guide research 50 years later. Black hole thermodynamics is no longer a curiosity. It is a cornerstone of theoretical physics, pointing toward the still unknown theory that unites gravity with quantum mechanics. For Hawking personally, this was a defining moment. It propelled him to international fame, not just among physicists, but among the public. The idea that black holes glow faintly in the darkness captured the imagination of scientists and non-scientists alike. It symbolized his ability to take abstract concepts and show their tangible consequences. From then on, Hawking was not merely a contributor to cosmology. He was one of its central figures. At a deeper level, black hole thermodynamics forces us to reconsider what we mean by information, order, and reality. If the entropy of a black hole measures its hidden degrees of freedom, what are those degrees of freedom? If the surface area encodes information, what does this say about the dimensionality of the universe? And if radiation allows black holes to vanish over time, what does this mean for permanence and stability in the cosmos? These questions remain open, but the framework that Hawking helped build continues to shape the search for answers. Existentially, there is something haunting in the idea that the darkest objects in the universe are not silent voids, but participants in the great thermodynamic flow. They consume, they radiate, and they obey the same deep principles that govern the boiling of water and the cooling of stars. In their apparent finality, they mirror our own lives. Finite, governed by irreversible processes, yet rich with hidden structure. Black hole thermodynamics tells us that even in the abyss, the universe preserves its order, its balance, and its laws. And as you consider these vast processes, let them ease the weight of your own concerns. The entropy of a black hole grows slowly over cosmic timescales. The universe itself keeps its secrets with patience beyond imagination. Whatever burdens you carried through the day, they are small beside the silent balance of gravity and heat at the edge of physics. Let that perspective be calming. You are part of a universe where even the most mysterious objects follow profound laws, and where rest is as natural as radiation from the horizon of a black hole. So allow yourself to rest now, letting the quiet rhythms of the cosmos carry you into sleep. Chapter 4. Hawking Radiation. Black Holes That Glow. By the early 1970s, Stephen Hawking had already helped push general relativity to its limits, making clear that singularities are not mathematical mirages and that black holes obey laws eerily similar to thermodynamics. The next leap came when he combined quantum field theory with curved spacetime and reached a conclusion that overturned the classical picture. Black holes emit thermal radiation. This quiet glow is unimaginably faint for astrophysical black holes, yet it is a robust prediction that arises when quantum fields are allowed to live on a spacetime containing an event horizon. In one stroke, black holes were promoted from cold, featureless endpoints of collapse to thermodynamic systems with temperature and entropy, and the old analogy became real physics. Classically, the event horizon is a one-way membrane. Light cones tilt inward so severely that even light cannot escape once it crosses the horizon. Combine this with the no-hair theorems and you get a stark portrait. After transient dynamics settle, a black hole is fully characterized by mass, electric charge, and angular momentum. Temperature and radiation seem irrelevant, but the quantum vacuum is not empty. Even in flat spacetime, fluctuations are always stirring every field. And in curved spacetime, the very definition of particles becomes observer-dependent. Hawking's calculation lives inside this framework of quantum fields on curved backgrounds. Quantize matter fields on the geometry formed by gravitational collapse, and then ask what a late-time observer at infinity actually sees. The standard intuitive picture invokes pairs of particles briefly materializing near the horizon. Usually the pair annihilates almost immediately. Near a horizon, however, One mode can propagate outward to infinity while its partner is trapped behind the horizon. To a distant observer, this looks like spontaneous emission. Energy conservation is preserved because the black hole's mass decreases by the amount radiated. The partner that falls in can be viewed as carrying negative energy relative to infinity. This story is helpful for intuition, but it is not the derivation. Hawking's computation relates in modes to out modes via Bogoliubov transformations and shows that late-time observers see a thermal spectrum. The perceived temperature is set by the surface gravity of the horizon and falls as the black hole's mass rises. Real black holes add refinements. The outgoing radiation is not perfectly black body because curvature outside the horizon partially scatters modes. The resulting gray body factors distort the spectrum and reduce the luminosity measured far away. Rotation introduces superradiance, in which certain bosonic waves are amplified when they scatter from the rotating geometry and extract spin energy. Electric charge and near-extremal conditions cool the horizon dramatically, pushing the temperature toward zero. Across all of these cases, the core message endures. Horizons and quantum fields together produce emission with a temperature governed by the near-horizon geometry. Because the temperature falls with increasing mass, stellar mass black holes are fantastically cold, far below the cosmic microwave background. Placed in an environment warmer than themselves, they absorb more than they emit. Only when the universe has cooled much further, or for much smaller holes, does evaporation dominate. Hypothetical primordial black holes, formed in the early universe from large density fluctuations, could be small enough that their Hawking flux today might be detectable. In that regime, evaporation accelerates as mass drops because the temperature climbs. A shrinking hole gets hotter, radiates faster, and races toward a brief, energetic finale. Hawking's result is one of the few rigorous predictions we possess about quantum fields on curved backgrounds. The calculation tracks modes that look vacuum-like in the far past, before the horizon forms, and then asks what those modes become for late-time observers. What counts as particles depends on how space-time is sliced into time and space, so the notion of vacuum is not absolute. A state that looks empty to one class of observers appears populated to another. The presence of a horizon makes that relativity of particles unavoidable and yields a clean, calculable thermal flux at infinity. A closely related phenomenon in flat spacetime clarifies the logic. The Unruh effect shows that a uniformly accelerating observer perceives the ordinary Minkowski vacuum as a thermal bath with a temperature proportional to the acceleration. Hawking's horizon temperature is the gravitational cousin of this effect. Where the Unruh temperature arises from acceleration through flat space, the Hawking temperature arises from a causal horizon in a curved spacetime. Horizons and heat travel together across gravitational settings, and the same mathematics that links acceleration, horizons, and thermality appears on both sides. Even though no instrument has directly detected Hawking quanta from an astrophysical black hole, the theoretical footing of the effect has only grown firmer. Independent derivations emphasize different aspects. Tunneling approaches model emission as barrier penetration and incorporate small back reaction corrections that nudge the spectrum away from perfect thermality. Euclidean methods relate temperature to periodicity in imaginary time by requiring smoothness of the Euclideanized geometry. The required periodicity fixes the inverse temperature. Simplified two-dimensional reductions capture universal near-horizon physics and reproduce the same flux. The convergence of these approaches shows that Hawking radiation is not a fragile artifact of one formalism, but a deep feature tied to horizon structure. Back reaction, the way the radiation drains mass and alters the geometry, is negligible for large holes, but grows as a hole shrinks. Early on, one can treat the geometry as fixed, but eventually the mass decreases, the temperature rises, and the emission accelerates. For a black hole of stellar mass, the total evaporation time is fantastically long, on the order of 10 to the 67th years, far beyond the current age of the universe. For much lighter holes, the timescales can be cosmologically short. Models of primordial black holes predict that those born below a critical mass would complete their evaporation today, perhaps producing brief bursts of high-energy gamma rays. The so-called trans-Planckian problem sparked early doubts. Modes that appear low-frequency to a distant observer correspond to extremely high frequencies when traced back toward the horizon, exceeding the Planck scale where known physics may fail. Would the result depend on untested microphysics? Analyses that modify the high-frequency dispersion relation, making it subluminal or superluminal, show the thermal character of the emission is strikingly insensitive to the details, provided the horizon is smooth. The kinematic origin of the effect, rooted in redshift near a horizon, appears robust against such ultraviolet deformations. Because genuine Hawking flux is so faint, experimentalists have turned to analog gravity systems that mimic horizon kinematics. Acoustic horizons in flowing fluids, horizons engineered in Bose-Einstein condensates, and optical analogs in nonlinear media create conditions where horizon-induced spontaneous emission can occur. Several groups have reported correlated phonon pairs in condensates and horizon-like optical scattering with spectra consistent with thermal emission. These platforms do not probe quantum gravity, but they reproduce the mechanism by which horizons create thermality, lending empirical plausibility to the underlying physics. Cosmology supplies a complementary arena. If primordial black holes formed shortly after the Big Bang, their mass spectrum would determine whether any survive. Those with initial masses below a certain scale would have evaporated already, potentially seeding the diffuse gamma-ray background or producing transient flashes. Space and ground-based observatories use such signatures to bound their abundance, ruling out large swaths of parameter space while leaving narrow windows still under investigation. Even null results are informative because they tie the viability of early universe scenarios to Hawking's prediction. One of the most striking conceptual payoffs of Hawking radiation is the way it reframed entropy in gravity. Black hole entropy scales with the area of the horizon, not the volume enclosed. That peculiar scaling suggested that the fundamental degrees of freedom of space-time might be encoded on surfaces, not in bulk regions. This insight inspired the holographic principle and later precise dualities in which a gravitational system in a higher dimensional space-time is equivalent to a non-gravitational quantum theory on its boundary. Within such frameworks, the thermal properties of black holes map onto ordinary finite temperature physics, giving statistical meaning to the thermodynamic quantities Hawking's work demanded. A further layer of clarity comes from the choice of quantum state. The Boole state looks empty to static observers at infinity, but is pathological at the horizon and cannot describe a hole formed by collapse. The Hartle-Hawking state represents a black hole in equilibrium with a bath of its own radiation and is appropriate in settings where radiation is reflected back, such as idealized cavities or anti-de Sitter spacetimes. The unruh state captures the realistic situation of a hole formed by collapse that radiates outward into nearly empty space with no incoming flux from infinity. Each state encodes a different physical scenario, and Hawking's calculation selects the unruh-like behavior relevant to astrophysical black holes. One can also sharpen the thermal character using ideas from statistical physics. In Euclidean formulations, regularity at the horizon requires imaginary time to be periodic, and that periodicity fixes a temperature in the same way the Kubo-Martin-Schwinger condition characterizes thermal states. Operationally, an idealized particle detector carried by a hovering observer just outside the horizon would register clicks with a rate determined by that temperature. Much as an unruh DeWitt detector, with constant acceleration through flat space, clicks at a rate set by the unruh temperature. These perspectives translate abstract field theory statements into the concrete language of detectors and counting events. The spectrum depends on what fields exist in nature. Emission rates differ for scalars, spin-1 photons, spin-2 gravitons, and neutrinos, and gray body factors weight their contributions differently as a function of frequency and angular momentum. At the low temperatures relevant to stellar mass holes, heavy particles are exponentially suppressed, so the flux is dominated by very light or massless degrees of freedom. As the temperature climbs in the late stages of evaporation, additional channels open, the spectrum hardens, and the luminosity rises sharply until the final brief phase. Observation in the wild remains difficult because ordinary astrophysical processes drown the signal. Accretion disks, jets, magnetic turbulence, and ambient radiation fields around black holes produce luminosities many orders of magnitude above the Hawking flux. Practical searches therefore focus either on analog systems in the laboratory or on the signatures of small relic black holes in the cosmos. Constraints from gamma-ray telescopes and air shower arrays limit the rate of final evaporation events and translate non-detections into upper bounds on how many primordial black holes could be lurking in specific mass windows. From a methodological perspective, the derivation's elegance is that it requires no full quantum theory of gravity. It is a semi-classical result, quantized matter on a classical space-time. That makes Hawking radiation a precious guidepost. Any candidate theory of quantum gravity must reproduce this effect in the appropriate limit and must explain the microscopic origin of black hole entropy, whose scaling with area rather than volume is so distinctive. In this way, Hawking's calculation acts as a boundary condition on deeper theories. Whatever the ultimate microphysics, it has to leave this thermality and this entropy law intact, where semi-classical reasoning should hold. The discovery also reshaped our picture of cosmic time. In the unimaginably distant future, after stars have burned out, galaxies have dispersed, and perhaps even protons have decayed, the last luminous beacons will be black holes. Over stupendous durations, they will radiate away their mass, leaving only low-energy quanta behind. In that view, Hawking radiation is not just a feature of horizons. It defines the closing chapter of cosmic history, a slow coda in which darkness quietly converts itself into light and then fades to the thinnest whisper. Existentially, the image is sobering and beautiful at once. Objects once thought eternal prove temporary, releasing their mass into the void in a patient exchange governed by deep symmetry between geometry and heat. Even the most absolute-seeming structures are woven into change, and the faint warmth leaking from a horizon tells us that endings are processes, not abrupt voids. As you let that thought settle, let it ease the weight of the day. If even black holes, the heaviest and darkest entities in the cosmos, can shed their burdens bit by bit, then so can you. Whatever you have carried, you can release it slowly and gently until you feel lighter. The universe unfolds with patience, and tonight you too can find rest within its quiet rhythm. Chapter 5. The Information Paradox. Can the Universe Lose Memory? When Stephen Hawking announced in the mid-1970s that black holes radiate, he also set off a conceptual earthquake. His calculation of thermal emission was accepted quickly, but the implications shook the foundations of physics. If black holes evaporate through Hawking radiation, and if that radiation is purely thermal, then all details about the matter that fell into the black hole are erased. When the black hole disappears completely, nothing remains to encode the lost information. The universe, it seemed, could forget. This scenario clashes violently with quantum mechanics, which insists that information is preserved in the evolution of physical systems. The tension between Hawking's prediction and quantum theory became known as the black hole information paradox, and it remains one of the central unsolved problems of fundamental physics. To understand why this paradox matters, we have to look at the principle of unitarity. In quantum mechanics, the state of a system evolves smoothly according to the Schrödinger equation. Probabilities may change, but the total information contained in the wave function is conserved. If you know the complete quantum state at one time, you can, in principle, reconstruct it at any other time. This reversibility is a cornerstone of quantum theory. Thermodynamics, by contrast, allows entropy to increase, but this increase reflects our limited ability to track every microscopic detail, not a literal destruction of information. Even when entropy grows, the underlying quantum state still evolves unitarily. Hawking's calculations seem to undermine this principle. His radiation had a thermal spectrum, meaning it depended only on the black hole's mass, charge, and spin. It carried no imprint of the specific matter that formed the black hole or later fell in. Two very different stars collapsing into identical black holes would, in Hawking's picture, produce indistinguishable radiation. When the black hole eventually evaporated, the detailed information about those stars would be gone forever. If true, this meant that quantum mechanics was incomplete, and that the universe could erase history in ways no laboratory experiment had ever shown. Initially, Hawking embraced this radical conclusion. He argued publicly that information loss was a fact of nature, and that quantum mechanics must be modified to accommodate it. This stance set him against many leading physicists, including John Preskill, Gerard Hooft, and Leonard Susskind, who were convinced that information must be preserved. What followed became known as the Black Hole War, a long-running debate that spanned conferences, seminars, and even wagers. Hawking and Kip Thorne bet that information was lost, while Preskill bet it was preserved. Decades later, Hawking would concede, but the journey to that point reshaped theoretical physics. One way to grasp the paradox is to think of a book thrown into a black hole. In principle, the quantum state of every atom in the book contains information. If the black hole erases it, the universe has lost more than just the text of the book. It has lost the fine-grained details of the matter's state. When the black hole radiates away, nothing in the outgoing thermal flux encodes the words. In ordinary thermodynamic processes, entropy grows because we ignore microscopic correlations, but the information still exists. In Hawking's case, the information seemed genuinely gone. The paradox grew sharper when physicists tried to apply the rules of quantum theory more carefully. The entanglement structure of Hawking radiation is especially troubling. In the standard picture, Each emitted quantum is entangled with a partner that falls into the black hole. As evaporation continues, the radiation outside is entangled with the interior, but once the black hole vanishes, there is no interior left. The external radiation, then, is left in a mixed state with no partner to purify it. This violates unitarity and leaves us with a universe that produces fundamentally unpredictable outcomes. Over the decades, several possible resolutions have been proposed. One idea is that information truly is lost, meaning quantum mechanics must be revised. This is the path Hawking originally favored, but such modifications would likely lead to observable violations of probability conservation in ordinary experiments, something never seen. Another idea is that black holes leave behind stable remnants that store the information. But remnants would have to hold arbitrarily large amounts of information in tiny packages, raising concerns about instability and uncontrolled particle production. The most popular line of thought is that the radiation is not perfectly thermal after all. Instead, subtle correlations between emitted quanta could encode the information. These correlations would be invisible in leading order calculations, but might emerge in a complete quantum gravity theory. In this view, Hawking's spectrum is only an approximation, and fine-grained details ensure unitarity. The challenge is to explain how this works while preserving the equivalence principle, which says that an observer falling across the horizon should encounter nothing unusual. In the 1990s, Susskind and 't Hooft argued that the resolution lies in holography. The entropy area relation, already suggested by Bekenstein and confirmed by Hawking's work, hinted that information about a volume of space might be stored on its boundary. This led to the holographic principle, the idea that the physics inside a region is fully encoded on its surface. In the context of string theory, this principle was given precise form through the ADS-CFT correspondence, which showed that a gravitational system in a higher dimensional space can be equivalent to a quantum field theory without gravity on its lower dimensional boundary. In this framework, black hole evaporation is unitary because the dual quantum theory is manifestly unitary. Still, holography does not eliminate all puzzles. It tells us that information is preserved globally, but not how it escapes from the horizon in a way consistent with local physics. This issue came to the forefront in the 2010s with the firewall paradox. If information does emerge in the radiation, then late-time quanta must be entangled with both early radiation and their partners behind the horizon. But quantum mechanics forbids a single system from being fully entangled in two independent ways. To resolve the conflict, one option is to break entanglement across the horizon, but that would replace the smooth experience of falling into a black hole with a wall of high-energy quanta, a firewall, violating the equivalence principle. Recent progress has come from new calculations in simplified models of gravity. These studies, often using techniques called replica wormholes, have been able to reproduce the so-called page curve. This curve describes how the entanglement entropy of the radiation should behave if information is preserved. It grows at first as the black hole radiates, peaks around the halfway point of evaporation, and then declines as information comes out in later quanta. Hawking's original calculation gave only a monotonically rising curve, implying information loss. The new methods, by contrast, recover the unitary page curve, suggesting that subtle non-local effects in quantum gravity allow information to escape. Despite this progress, the mechanism by which information escapes remains elusive. Does it leak out gradually in correlations among quanta? Is it encoded holographically on the horizon? Do wormhole-like connections carry it outward in ways we only partly understand? Each proposal challenges some aspect of our intuitions about locality, causality, or smoothness of spacetime. What unites them is the conviction that Hawking's prediction, though correct at the semi-classical level, must be refined by quantum gravity. The information paradox has been fertile ground for new ideas because it sits at the intersection of relativity, quantum theory, and thermodynamics. It forces us to ask whether space-time itself is emergent from more fundamental degrees of freedom, whether locality is approximate rather than exact, and whether horizons are as impermeable as they seem. The paradox also shows how a thought experiment, throwing matter into a black hole and watching it evaporate, can probe physics far beyond our current experimental reach. For Hawking himself, the paradox was not just a technical problem, but a test of scientific courage. He was willing to stake his reputation on the claim that information is lost, even though it clashed with mainstream opinion. Later in life, he conceded the bet, admitting that information might be preserved after all. But his willingness to follow the mathematics to a radical conclusion is what gave the paradox its power. It inspired generations of physicists to explore the edges of theory, to seek unification, and to imagine physics beyond what we can currently measure. Existentially, the information paradox is more than a debate about quanta. It touches on the question of memory itself. If the universe can forget, what does that mean for meaning and continuity? If information is preserved, then every trace of existence is woven into the fabric of reality, indelible even when transformed. The paradox forces us to confront whether impermanence is absolute or whether beneath it lies a permanence of pattern. And as you let these questions linger, allow them to ease the day's concerns. The paradox is not solved, and perhaps it never will be fully resolved. But that is part of its beauty. In a universe where even black holes challenge our understanding, your own uncertainties can rest quietly. The cosmos carries them, just as it carries its deepest mysteries, into the patient unfolding of time. Let that perspective calm you. Tonight, you can set aside what cannot yet be answered and sink into rest as the universe itself holds its secrets gently in the dark. Chapter 6. Imaginary Time and the Shape of the Universe. Among Stephen Hawking's many contributions to theoretical physics, one of the most striking and philosophically provocative was his use of the concept of imaginary time. At first glance, the phrase seems nonsensical. Time is what we measure with clocks, the steady ticking that separates past from future. How could time be imaginary? Yet Hawking used this mathematical tool to propose a new way of thinking about the origin of the universe, one that avoids the infinite singularities predicted by classical general relativity. By turning time into a spatial dimension in certain calculations, he suggested that the universe may be finite but without boundaries, much like the surface of a sphere. The notion of imaginary time emerges from a technique widely used in physics called Wick rotation. In quantum field theory and statistical mechanics, calculations often become simpler if one substitutes real time with imaginary values, effectively rotating the time axis into the complex plane. This turns oscillating exponential functions into decaying ones, smoothing out divergences and making integrals converge. After performing the calculation, one can rotate back to real time. In most contexts, this is a purely mathematical trick with no claim to physical reality. But Hawking realized that in cosmology, imaginary time might describe something about the actual structure of spacetime itself. Classical general relativity predicts singularities in the past. If the universe has been expanding since the Big Bang, then tracing it backward implies a point of infinite density and curvature. At such a singularity, the laws of physics break down. This is unsatisfactory not only scientifically but philosophically, for it suggests a beginning outside the scope of explanation. Hawking's proposal was to consider the universe in imaginary time near what would otherwise be a singularity. By making this substitution, the equations that describe spacetime take on a Euclidean character. Instead of a sharp boundary where time starts, one finds a smooth, rounded geometry. To visualize this, consider the surface of the Earth. If you travel southward, you eventually reach the South Pole. But the pole is not a boundary where the Earth stops. It is simply a point where one direction ends and another begins. The surface is finite, yet without edges. In Hawking's picture, imaginary time plays a similar role. Near the origin of the universe, time behaves like a spatial coordinate, so the beginning of the universe resembles the smooth cap of a sphere, not a singular edge. The universe is finite in extent, but without a boundary where the laws of physics would fail. This idea was developed in Hawking's collaboration with James Hartle, leading to the no-boundary proposal. The proposal states that the universe is described by a quantum wave function defined over possible geometries, and that these geometries include compact Euclidean ones without boundaries. Imaginary time is the mathematical key that allows such geometries to exist smoothly. While Chapter 7 will focus on the broader no-boundary proposal, it is important here to recognize that the very use of imaginary time was the conceptual leap that made it possible. One of the scientific motivations for this approach was to reconcile quantum mechanics with cosmology. Quantum mechanics is naturally formulated in Euclidean time because probabilities and path integrals are easier to compute when oscillatory phases become decaying exponentials. Hawking and Hartle applied this logic to the universe as a whole, treating its history as a kind of quantum path integral over geometries. Imaginary time eliminated the singularity and provided well-behaved contributions to the integral. The outcome was a model in which the universe could arise spontaneously without requiring a sharp initial condition. Critically, imaginary time does not mean that we literally experience time as imaginary. Our everyday sense of past, present, and future corresponds to real time. Imaginary time is a coordinate transformation that reveals deeper structure in the mathematics. What makes Hawking's use distinctive is that he entertained the possibility that imaginary time reflects something physically real about the universe's geometry at its earliest stages. Near the Planck epoch, when quantum gravity dominates, our familiar conception of time might simply not apply. The smooth Euclidean character of space-time and imaginary time could replace the singular origin of real time. The implications of this are profound. If the universe has no boundary in imaginary time, then asking what came before the Big Bang is meaningless, just as asking what lies south of the South Pole is meaningless. Time as we know it simply does not extend further back. The universe is self-contained, finite yet unbounded, with no external cause or beginning. This picture does not eliminate the need for explanation. One must still account for why the laws of physics are as they are, but it removes the conceptual problem of a singular starting point. Imaginary time also changes how we think about the shape of the universe. In real time, we experience expansion, galaxies receding, space stretching, time flowing forward. In imaginary time, the geometry is static and compact, more like a sphere than a line. This duality suggests that the universe may be understood as a four-dimensional object with both Euclidean and Lorentzian aspects, depending on how one slices it. Our flow of time is one perspective, but beneath it lies a structure where time and space are more deeply unified. While elegant, Hawking's use of imaginary time is not without challenges. Many physicists treat it as a calculational device rather than a literal description. The transition between imaginary and real time is not fully understood in quantum gravity, and the no-boundary proposal has faced technical difficulties in defining probabilities unambiguously. Some cosmologists favor alternative models, such as eternal inflation or bouncing universes, which handle the singularity differently. Nevertheless, imaginary time remains one of the most creative attempts to merge mathematical consistency with physical interpretation. Over the years, the concept has inspired both scientific and popular imagination. In his book A Brief History of Time, Hawking wrote that if the universe is finite but without boundary, it has no beginning and no end. It simply is. This statement captivated readers because it framed cosmology in existential terms. Imaginary time offered a scientific way to envision a cosmos that requires no external cause, no creation event, no before. Instead of confronting a singular wall, we encounter smoothness. The universe folds back on itself, and our questions about ultimate origins are transformed. From a technical perspective, imaginary time has also been useful in black hole physics. Euclidean methods, which rely on imaginary time, are used to compute black hole entropy and temperature. The requirement that Euclidean space-time be smooth at the horizon fixes the periodicity of imaginary time, which in turn yields the Hawking temperature. Thus, the same mathematical trick underlies both black hole thermodynamics and Hawking's cosmological ideas. This coherence suggests that imaginary time is more than a curiosity. It is a unifying concept across gravitational physics. Imaginary time has also found resonance in discussions about the arrow of time. In real time, entropy increases, and we perceive a direction from past to future. In imaginary time, there is no arrow. The geometry is symmetric, without a privileged direction. This symmetry may help explain why the universe began in a low entropy state. In imaginary time, there is no distinction between before and after, so the asymmetry of time emerges only when real time takes over. The arrow of time, then, could be a derived property rather than a fundamental one. For Hawking, the idea of imaginary time was a way to tame the infinities that threatened to break physics. Instead of accepting a singularity where the laws failed, he used the mathematics of Euclidean spacetime to propose a consistent, boundary-free universe. This was not a final answer. Quantum gravity remains elusive, but it was a bold attempt to extend our reach into the earliest moments of the cosmos. It showed how far imagination, grounded in mathematics, can take us. Existentially, imaginary time is both humbling and liberating. It suggests that our sense of beginnings and endings may be parochial, tied to the way we experience real time. The universe itself may have no sharp start, no edge, no outside. It may simply be timeless in its foundation. In this view, our questions about what came before the Big Bang dissolve, not because they are answered, but because they were never meaningful to begin with. And as you contemplate this vision, allow it to soften the edges of your own day. If the cosmos itself flows without a beginning or end, then you too can release the need for closure tonight. There is no singular boundary between wakefulness and rest, only a smooth transition, a gentle rounding off. Let the thought of a universe without edges cradle you, and let yourself drift calmly into sleep, carried by the timeless quiet of imaginary time. Chapter 7. The No-Boundary Proposal, Hartle-Hawking State. If Hawking's idea of imaginary time opened a new way to think about the beginning of the cosmos, the no-boundary proposal developed with James Hartle was its boldest realization. Known as the Hartle-Hawking state, this model aimed to answer one of the deepest questions in cosmology. How did the universe begin? The standard Big Bang picture describes a singular origin, where density and curvature become infinite. But singularities are not places. They are breakdowns of the laws that should describe them. Hawking and Hartle sought a model that would avoid singularities and instead produce a self-contained universe, finite yet without edges. The essence of the no-boundary proposal is that the universe's wave function, which encodes the probabilities of different histories, can be defined by summing over all possible compact Euclidean geometries. In this view, the early universe is not described by a singular point in real time, but by a smooth, rounded geometry in imaginary time. Just as the Earth's surface is finite yet without a boundary, so too the universe would be finite in extent, but without an edge where time begins. The metaphor Hawking often used was the South Pole. Asking what happened before the Big Bang is like asking what lies south of the South Pole. It is not a meaningful question because the geometry simply closes off smoothly. The proposal arose at the intersection of quantum mechanics, general relativity, and cosmology. Quantum mechanics tells us that systems are described by wave functions, evolving in time according to deterministic equations but yielding probabilistic outcomes. General relativity tells us that space-time itself is dynamical, shaped by matter and energy. Bringing these together means treating the universe as a quantum system, with a wave function defined not over particles in space-time, but over possible spacetimes themselves. The no-boundary wave function is precisely this: a functional that assigns amplitudes to different geometrical histories of the universe. To make this concrete, Hartle and Hawking formulated the wave function as a path integral, a sum over possible geometries weighted by the exponential of the Euclidean action. This was inspired by Feynman's path integral in quantum mechanics, where the probability amplitude for a particle to move from one point to another is obtaining over all possible paths, each weighted by a phase. For the universe, one sums not over paths but over geometries. Imaginary time is the crucial element because it makes the geometries compact and the integral mathematically manageable. Without imaginary time, the integrals diverge. With it, they yield smooth, finite contributions. The resulting picture is that the universe did not begin with a bang, but with a smooth, rounded cap in imaginary time. From this Euclidean regime, the universe transitioned into the Lorentzian regime we inhabit, where time behaves as we experience it. In this view, the cosmos has no boundary in the past. Instead of an edge where physical law fails, there is continuity. This does not mean that time existed forever. Rather, it means that the notion of before is not defined. The universe is self-contained, with no need for external conditions. One of the strengths of the no-boundary proposal is that it naturally predicts inflation, the brief period of rapid expansion that solves many puzzles of cosmology. When the path integral is evaluated for simple geometries, the most probable histories are those that begin with a short period of exponential growth. This aligns the proposal with observations of the cosmic microwave background, which are consistent with inflationary models. Thus, the no-boundary idea is not just philosophical, it has explanatory power for real data. The proposal also shifts how we think about causality and initial conditions. In classical physics, the state of a system at one moment determines its state at the next. To know the universe's history, we would need initial data specified at its beginning. But if the beginning is a singularity, such data cannot be given. The no-boundary proposal avoids this by eliminating the boundary altogether. Instead of initial conditions, the universe is described by the no-boundary wave function, which assigns probabilities to entire histories. The need for an external input disappears. This self-contained character of the universe resonated with Hawking's philosophical sensibilities. In public lectures, he often emphasized that if the universe has no boundary, then it has no beginning and no need for a creator. This statement was not meant as theology, but as physics. If the laws are self-sufficient, then the universe can be understood entirely from within. In that sense, the no-boundary proposal was as much about intellectual completeness as it was about technical cosmology. Despite its elegance, the proposal has faced challenges. The path integral over geometries is difficult to define rigorously. Not all geometries contribute positively, and the measure of the integral is subtle. Critics have argued that the no-boundary wave function may not be mathematically well-defined without additional restrictions. Others have suggested alternative boundary conditions, such as the tunneling proposal advanced by Alexander Vilenkin, which envisions the universe emerging from nothing through a quantum tunneling event. These alternatives produce slightly different predictions for inflationary models and the structure of the cosmic microwave background. Nevertheless, the no-boundary proposal has remained influential. It continues to inspire refinements in quantum cosmology and has been adapted to frameworks like string theory and loop quantum gravity. Recent work on semi-classical methods and holographic cosmology has revisited the idea, suggesting that the no-boundary wave function may connect to deeper principles about holography and entropy. In this way, Hawking's imaginative leap still guides modern research. It is also important to note what the no-boundary proposal does not claim. It does not deny that the universe had an early hot dense phase. Rather, it reframes how that phase is understood in quantum terms. Nor does it assert that imaginary time is literally experienced. It is a mathematical representation that captures the geometry of the earliest universe. The proposal is less about what we would see if we traveled back to the beginning and more about what the equations tell us when applied consistently. From a scientific standpoint, the proposal's value lies in its coherence. It shows that it is possible to formulate a model of the universe that avoids singularities, incorporates quantum principles, and makes contact with cosmological observations. Even if refinements are needed, the framework demonstrates that questions about the universe's origin can be approached with physics rather than deferred to metaphysics. On a deeper level, the no-boundary proposal reshapes how we imagine the cosmos. We often think in terms of origins and causes, searching for a first event or a prime mover. The no-boundary view denies us that comfort. Instead, it offers a universe that is finite, but without edges, self-contained, and complete. This challenges our intuitions, but also frees us from the paradoxes of singular beginnings. The universe does not need a before, it simply is. Philosophically, this raises questions about time itself. If time as we know it emerges only after the transition from imaginary to real time, then our most basic categories, past, present, future, are emergent features, not fundamental truths. The deep structure of the universe may be timeless in its foundation. What we perceive as the flow of time could be a secondary phenomenon, arising only when the universe enters the Lorentzian regime. For Hawking, The no-boundary proposal represented both scientific ambition and personal vision. It showed his ability to use mathematics not just as a tool for calculation, but as a canvas for reimagining reality. His willingness to consider imaginary time as more than a trick and to build an entire cosmological model from it exemplifies the blend of rigor and imagination that defined his career. Existentially, the no-boundary proposal suggests that we are inhabitants of a universe that requires no external explanation. There is no edge beyond which lies nothingness. There is only continuity. To live in such a cosmos is to live in a world that contains within itself the reasons for its being. This vision is both unsettling and deeply calming. And as you let these ideas drift through your thoughts, let them bring you peace. If the universe itself can be smooth and without boundaries, then so too can your mind tonight. There is no sharp edge where you must stop. There is only the gentle rounding off into rest. Let yourself follow that curve into calm as the cosmos itself folds quietly into timelessness. Chapter 8. Chronology Protection. Why Time Travel May Be Impossible. Time travel has fascinated humans for centuries, long before Einstein revealed that space and time are flexible and dynamic. In myths and stories, people imagine revisiting the past or glimpsing the future, changing outcomes or fulfilling destiny. In physics, the concept is both alluring and troubling. Einstein's general relativity describes space-time as a malleable fabric curved by energy and mass, and within this theory lie solutions that seem to permit closed time-like curves, paths through space-time that loop back on themselves, allowing an object or observer to return to an earlier point in their own history. The possibility of such curves has led to serious scientific debate. Could time travel really happen? Stephen Hawking was skeptical. He believed that the logical consistency of the universe demanded safeguards against paradoxes. In 1992, he gave this conviction a name: the chronology protection conjecture. It was his witty but serious attempt to argue that the laws of physics prevent macroscopic time machines. In his words, the laws of physics conspire to prevent time travel on a macroscopic scale. To understand what was at stake, it helps to recall that general relativity admits a wide variety of exotic spacetimes. Kurt Gödel, a logician best known for his incompleteness theorems, discovered in 1949 a solution to Einstein's equations that describes a rotating universe filled with matter. In this model, closed time-like curves naturally exist. One could in principle travel along such a curve and arrive back at one's own past. Other proposed scenarios include the Tipler cylinder, a hypothetical, infinitely long rotating cylinder of dense matter that could generate closed time-like loops, and wormholes, tunnels connecting distant regions of space-time. In many of these constructions, if one manipulates the geometry correctly, paths through the structure allow effective backward time travel. At first glance, nothing in general relativity forbids such geometries. Einstein's equations are differential equations, and given exotic enough distributions of energy and momentum, they yield exotic spacetimes. But not all mathematically consistent solutions are physically realizable. For instance, Gödel's universe requires global rotation inconsistent with our observed cosmos. Tipler cylinders must be infinitely long, something no real object could be. Wormholes require exotic matter, a form of material with negative energy density, to remain open. While quantum field theory allows negative energy densities in limited circumstances, such as the Casimir effect, sustaining them at macroscopic scales seems implausible. The challenge is not only practicality, but logical consistency. time machines generate paradoxes. The grandfather paradox is the most famous example. If you traveled back in time and prevented your ancestor from existing, you would remove your own reason for traveling in the first place. More subtle are consistency paradoxes involving information. If a message is sent into the past and used to create itself, information appears from nowhere, violating the principle that causes precede effects. These paradoxes suggest that something deeper must forbid closed time-like curves from becoming physical realities. Hawking proposed that the safeguard lies in quantum physics. When spacetimes threatening to develop closed time-like curves are examined with quantum field theory, calculations often show that quantum fluctuations become uncontrollably large near the would-be time machine. The expectation value of the stress-energy tensor diverges at the boundary of chronology violation. This energy buildup would curve spacetime so strongly that the closed loops are destroyed before they can form. In effect, the universe defends itself. Quantum mechanics, usually thought to allow uncertainty and strangeness, here acts as a guardian of consistency. This logic resembles another guiding principle in relativity, the cosmic censorship conjecture, which posits that singularities are always hidden behind horizons so that observers never directly encounter them. Just as cosmic censorship prevents naked singularities from undermining predictability, chronology protection prevents causal loops from undermining determinism. Both are not yet proven theorems, but conjectures supported by strong evidence and motivated by the demand for consistency in physics. The semi-classical analyses that support chronology protection are illuminating. In spacetimes where closed time-like curves threaten to appear, vacuum fluctuations are not gentle ripples but violent storms. Quantum fields become infinitely excited as one approaches the chronology horizon, the boundary beyond which closed loops would exist. The back reaction of this energy cannot be neglected. It forces space-time to rearrange itself in ways that close off the loophole. This is why Hawking argued that time machines are unstable. Even if general relativity permits them mathematically, quantum effects destabilize them physically. The chronology protection conjecture does not forbid all speculation. Tiny, transient violations of chronology might exist at microscopic scales, hidden within quantum foam at the Planck length. But large, stable, traversable time machines, the kind beloved by science fiction, would be ruled out. For Hawking, this was a relief. He quipped that one reason we should believe in chronology protection is the lack of tourists from the future. If time travel were possible, wouldn't we have met visitors from centuries ahead? His humor underscored a serious point. Nature seems to enforce causality. At the same time, other physicists have considered alternative possibilities. Igor Novikov proposed the self-consistency principle, which suggests that if closed time-like curves exist, events along them must be globally self-consistent. In this view, paradoxes are avoided not because time travel is impossible, but because the universe arranges events so that contradictions cannot occur. You might travel back in time, but your actions would always be part of history as it already happened. This is a logically consistent framework, but it implies a strange fatalism. Free will becomes illusory if your journey to the past is already woven into the tapestry of events. Hawking found such solutions unsatisfying. He preferred the cleaner safeguard of chronology protection, where quantum effects prevent paradoxes before they arise. His perspective reflected both physical reasoning and philosophical taste. Physics should not merely accommodate paradoxes with clever consistency conditions. It should prevent them. The broader significance of chronology protection is how it points toward quantum gravity. Both black hole evaporation and time machine scenarios show that general relativity alone cannot answer the hardest questions. Quantum effects matter, even when space-time curvature is gentle. Hawking radiation revealed that black holes are not eternal, while chronology protection suggested that time machines are unstable. In both cases, quantum field theory in curved spacetime supplies corrections that restore logical coherence. In the search for a full quantum theory of gravity, chronology protection offers a guiding principle. Any consistent theory must either enforce it or provide an alternative mechanism that ensures consistency. String theory and loop quantum gravity both contain structures that appear to safeguard causality. In holographic dualities, causality in the boundary quantum field theory forbids causal loops in the bulk gravitational theory, reinforcing the idea that chronology protection is a natural feature of a deeper framework. Still, the debate is not closed. Some exotic spacetimes evade obvious divergences, at least in simplified models. Could stable time machines exist in corners of the theory we do not yet understand? Could the quantum fluctuations be tamed by new physics? These questions remain open, though the consensus leans toward Hawking's intuition. Time travel to the past is forbidden, not by decree, but by the self-consistency of nature's laws. The cultural impact of Hawking's conjecture is notable. While popular culture continues to imagine time machines, science grounds us in more sober possibilities. This does not diminish wonder but reshapes it. The universe may not allow backward journeys, but it still offers cosmic expansion, gravitational waves, black hole mergers, and quantum entanglement. All phenomena more astonishing than fiction. Hawking's wit and clarity helped bridge these two worlds, reminding us that imagination and rigor can coexist. Existentially, chronology protection gives us something comforting, the assurance that time's arrow is stable. The past cannot be rewritten, and causality is preserved. This permanence means our memories are anchored, our choices matter, and the coherence of life is maintained. While we may long for do-overs, the structure of time gives weight to our actions and meaning to our histories. And as you let that thought rest in your mind, allow it to calm the day's turbulence. Whatever has unfolded cannot be undone, but it can be accepted. The future remains open, not to paradox, but to possibility. Like the universe itself, you are carried forward by the flow of time, steady and secure. Tonight, let go of regrets, release the loops of thought that circle back on themselves, and allow yourself to move smoothly into rest. The arrow of time guides you gently onward, and in that certainty, you can close your eyes and drift peacefully into sleep. Chapter 9. Primordial Black Holes and Dark Matter. Black holes are usually thought of as the end states of stellar evolution. When massive stars exhaust their fuel, gravity overwhelms all other forces, and collapse creates a singular region of spacetime from which nothing can escape. But in the early universe, long before the first stars formed, conditions were radically different. The cosmos was hot, dense, and filled with violent fluctuations. In that environment, it is possible that black holes formed directly from the primordial soup itself. These are called primordial black holes, and they are distinct from the stellar and supermassive black holes we observe today. Stephen Hawking was one of the first to recognize their importance, not only as possible relics of the early universe, but also as potential candidates for dark matter, the unseen mass that shapes galaxies and cosmic structure. The idea is rooted in the physics of the Big Bang. In the first fractions of a second, the universe expanded rapidly, But the density was so enormous that even small fluctuations in matter could collapse under their own gravity. If a region of space had just the right conditions, denser than average, above a critical threshold, it could overcome pressure forces and collapse into a black hole. The mass of the black hole would depend on the scale of the fluctuation. Smaller fluctuations could produce tiny black holes, while larger ones could create objects of planetary or stellar mass. Unlike ordinary black holes, primordial ones are not the product of dying stars. They are fossils from the infant universe. What makes primordial black holes fascinating is the wide range of masses they could have. Some could be as small as a mountain, with masses comparable to asteroids but compressed into microscopic radii. Others could weigh as much as planets, stars, or even more. Their formation would depend on conditions such as the spectrum of density fluctuations, phase transitions in the early universe, or the dynamics of cosmic inflation. Because they are not tied to stellar processes, they could exist in mass ranges where no ordinary astrophysical black holes form. Hawking's work on black hole radiation immediately connected with this idea. He realized that small primordial black holes would evaporate quickly through Hawking radiation. A black hole with mass around 10^² kilograms, roughly the mass of a mountain, would evaporate on timescales comparable to the current age of the universe. Such an object, if formed at the Big Bang, would be reaching the end of its life today, releasing a burst of high-energy radiation in its final moments. Larger primordial black holes would still be around, slowly radiating but far from complete evaporation. The possibility of detecting such bursts or of constraining their abundance through the absence of signals became one of the first ways to test Hawking's ideas. At the same time, astrophysicists were grappling with the puzzle of dark matter. Observations of galaxies and clusters showed that visible matter accounted for only a fraction of the gravitational pull. Something unseen was holding galaxies together, bending light through gravitational lensing and shaping the cosmic web. Particle physicists proposed new particles, such as weakly interacting massive particles, or WIMPs. But another possibility was that dark matter consisted of compact, non-luminous objects. Primordial black holes, being massive but invisible except through gravity, fit the bill. The attraction of primordial black holes as dark matter is that they require no new particles beyond those we already know. If conditions in the early universe favored their formation, they could have survived in large enough numbers to account for the missing mass. Their gravitational influence would mimic that of dark matter, clustering around galaxies and shaping cosmic evolution. Hawking's recognition of this possibility made primordial black holes a bridge between early universe cosmology, black hole physics, and the dark matter problem. Testing this idea, however, is complex. Primordial black holes interact gravitationally, but otherwise they are elusive. If they are too small, they would have evaporated already, potentially leaving behind gamma rays or other high-energy relics. If they are too large, their gravitational effects on astrophysical systems should be detectable. Astronomers have used many strategies to search for them. Gravitational lensing is one of the most powerful. When a compact object passes in front of a background star, it can briefly magnify the star's light. Surveys of stars in the Magellanic Clouds in the Milky Way have looked for such microlensing events. The absence of large numbers of these events has ruled out primordial black holes in certain mass ranges. Other constraints come from cosmic microwave background measurements. Black holes accrete matter and radiate energy, which could disturb the delicate balance of the early universe's radiation field. If primordial black holes were too abundant, the imprint they left would conflict with the observed smoothness of the microwave background. Observations from satellites like Planck have been used to place tight bounds on how many primordial black holes could exist. Yet, despite these constraints, certain mass windows remain viable. Black holes of asteroid mass, lighter than a planet but heavier than small comets, are still possible candidates. Likewise, very heavy black holes, hundreds or thousands of times the mass of the Sun, have not been completely excluded. Intriguingly, the detection of gravitational waves by LIGO has reopened interest in primordial black holes. The first signals came from black hole mergers of around 30 solar masses, heavier than most stellar remnants known at the time. Some physicists suggested that these could be primordial in origin, though stellar explanations remain likely. Theoretical models continue to explore how inflationary physics could generate density fluctuations that seed primordial black holes. Certain inflation models naturally predict enhanced fluctuations at specific scales, potentially leading to black hole formation. Phase transitions in the early universe, where symmetries broke and fields shifted, could also generate conditions ripe for collapse. These scenarios connect black holes to the deepest questions about high-energy physics, unification, and the structure of space-time at its earliest moments. If primordial black holes make up some or all of dark matter, their discovery would revolutionize physics. Instead of requiring entirely new particle species, the mystery of dark matter could be explained by gravitational relics of the Big Bang. This would unify cosmology and black hole physics in an elegant way, fulfilling Hawking's instinct that the boundaries between disciplines often hide the most profound insights. Even if primordial black holes are only a small fraction of dark matter, they could still play a role in cosmic history. They may have acted as seeds for supermassive black holes at galactic centers, accelerating the growth of structure. They might have influenced reionization, the epoch when the first stars and galaxies lit up the universe. Their evaporation, if it occurred, could have left imprints in cosmic radiation backgrounds or in the abundance of light elements. Each possibility extends the reach of Hawking's original insight, that tiny black holes born at the dawn of time might still shape the universe today. The search continues with ever greater precision. Future gravitational wave detectors, surveys of microlensing in distant galaxies, and high-energy astrophysical observatories will refine the parameter space. Whether primordial black holes turn out to be the dark matter or not, the pursuit deepens our understanding of both early universe physics and gravitational phenomena. Hawking's role in this story is pivotal. He not only introduced the idea of primordial black holes, but also tied their fate to the evaporation process he discovered. His calculations showed that their existence could be probed indirectly, linking the tiniest scales of quantum gravity with the largest structures of cosmology. In doing so, he exemplified his gift for connecting distant realms of physics into a coherent picture. Existentially, primordial black holes remind us that the universe carries fossils of its earliest moments. Hidden in the darkness may be objects older than stars, silent witnesses to creation itself. If they make up the dark matter, then galaxies, stars, planets, and life all owe their structure to these primordial seeds. We live in a cosmos whose present is sculpted by remnants of its birth. And as you rest with that thought, let it calm your mind. The universe remembers its own infancy through these ancient black holes, just as you carry memories of your own beginnings. Whether or not we ever find them, the possibility itself tells us that the past is never entirely gone. Tonight, you can set aside the day, knowing that the cosmos holds its history quietly and that in its quiet presence, you too can drift gently into sleep. Chapter 10. Hawking's Legacy, Top-Down Cosmology and Beyond. As Stephen Hawking's career advanced into its later decades, he continued to push against the boundaries of cosmology, not only refining earlier insights about black holes and the origin of the universe, but also venturing into new proposals that would shape discussions long after him. Among his most distinctive contributions was the idea of top-down cosmology, a framework that shifted how physicists think about the relationship between quantum theory and the history of the cosmos. This approach, developed with Thomas Hertog, challenged the traditional picture of a universe with a single, well-defined past, and instead suggested that multiple histories could coexist, with the past itself dependent on how we observe the present. In many ways, it was the culmination of Hawking's life's work, blending relativity, quantum mechanics, and philosophical imagination into a vision that redefined our place in the cosmos. The starting point is the recognition that cosmology is not like ordinary physics. In laboratory experiments, we set up initial conditions and watch how a system evolves. The laws of physics then determine the outcomes. But when the system is the universe itself, there is no external experimenter who can fix the initial conditions. Classical cosmology assumes that the universe began in some specific state, such as a singular Big Bang, or the smooth geometry proposed in the no-boundary condition, and then evolved forward. In this bottom-up approach, one specifies the beginning and calculates the rest. Hawking and Hertog proposed a reversal. Instead of assuming that the universe had one unique beginning, they suggested that it is better described by summing over many possible histories, each weighted by their probability amplitude. This is a direct application of Feynman's path integral philosophy to cosmology. Just as a particle does not take a single path but explores all paths, the universe may not have a single past, but rather a quantum superposition of many possible pasts. The top-down approach means we start from the present with its observed properties, and then trace backward through all histories compatible with those properties. The universe's past, in this view, depends on what we measure in the present. This shift has both technical and philosophical implications. On the technical side, it reframes how we compute the probabilities of different cosmological scenarios. Instead of asking what the universe inevitably looked like at its origin, we ask what configurations of the past are consistent with the universe we see now. The mathematics employs path integrals over geometries, building on the same Euclidean techniques that underpinned Hawking's earlier work with the no-boundary proposal. But where the no-boundary idea posited a specific smooth geometry at the origin, top-down cosmology embraces a spectrum of possibilities, reflecting the probabilistic essence of quantum mechanics. Philosophically, the proposal mentions the very notion of a fixed past. In classical history, the past is determinate. Events occurred in one particular way. In quantum cosmology, however, the past may be as uncertain as the future until it is observed. Hawking often emphasized that the wave function of the universe encodes all possible histories and that observation selects among them. In this sense, cosmology becomes participatory. Our measurements of the present help determine which histories are relevant, collapsing the multitude of potential pasts into the one that fits our observations. This idea aligns with a broader theme in quantum physics, the inseparability of observer and system. In the double-slit experiment, particles take many paths until an observation singles out an outcome. Hawking extended this logic to the cosmos itself. The universe may contain many possible paths in its early history, but the reality we observe today is shaped by the act of observation. In top-down cosmology, there is no single, observer-independent account of the universe's origin. Instead, the past is conditional, tied to the present in a feedback loop that blurs the arrow of explanation. Top-down cosmology also addresses puzzles about the apparent fine-tuning of the universe. Many features of our cosmos seem delicately balanced to allow for the existence of galaxies, stars, and life. Classical cosmology often frames this in terms of initial conditions. The universe began with just the right properties. But in a top-down framework, such fine-tuning arises naturally. Out of the many possible histories, we find ourselves in one consistent with our existence. Not because the universe was set up that way from the start, but because only those histories compatible with observers like us are realized in our measurements. This is not quite the anthropic principle as usually stated, but it resonates with it. Our perspective as observers is built into the structure of quantum cosmology itself. Hawking and Hartle elaborated these ideas in the context of inflationary cosmology. Inflation, the exponential expansion of the early universe, is an established component of modern cosmology, supported by the smoothness of the cosmic microwave background and the distribution of large-scale structure. But in some models, inflation can continue eternally, generating an infinite multiverse of pocket universes with varying properties. This picture raises conceptual and mathematical difficulties, including how to assign probabilities across an infinite ensemble. Hawking was critical of such unbounded multiverse scenarios. Top-down cosmology provided an alternative. By summing over histories that match our current observations, it avoids the infinities of eternal inflation while still accommodating quantum variety. The idea also connects to holography, the principle that physics in a volume of space can be described by data on its boundary. In some formulations, top-down cosmology can be reinterpreted through holographic dualities, where the probabilities of different universes correspond to correlation functions in a lower-dimensional quantum theory. This link reinforces the sense that the universe is not a machine unfolding from a single origin, but a web of probabilities shaped by fundamental quantum rules. Critics have raised objections, noting that top-down cosmology is difficult to test directly. Its reliance on path integrals over geometries makes calculations technically challenging, and the connection between observation and history remains conceptually murky. Still, the proposal is valuable precisely because it forces cosmologists to question assumptions. Rather than taking initial conditions as given, it treats them as emergent. Rather than separating physics from observation, it acknowledges their entanglement. Hawking's goal was never to provide final answers, but to push the field toward deeper questions, and top-down cosmology achieved exactly that. Beyond top-down cosmology, Hawking's later work engaged with broader themes. He continued to refine arguments about information loss in black holes, eventually conceding that information may be preserved, but pressing on how this occurs in detail. He explored the role of holography in cosmology, speculated about the nature of fundamental laws, and popularized science in ways that brought cosmology into the cultural mainstream. His collaborations with students and colleagues ensured that his influence extended well beyond his own publications. The legacy of his ideas is not limited to the technical literature. Hawking exemplified how a scientist can balance rigor with imagination. He was unafraid to propose bold conjectures: chronology protection, no-boundary cosmology, top-down histories, even when evidence was incomplete. He saw science as a process where daring speculation, guided by mathematics, could open new horizons. Many of his proposals remain unproven, and some may ultimately be replaced, but their influence endures in the way they reframe questions. Existentially, Hawking's vision was one of continuity and self-containment. From imaginary time to top-down cosmology, his work suggested that the universe requires no external cause or boundary. It is a closed system, governed by laws that encompass its origin and fate. This perspective invites us to see ourselves not as separate from the cosmos, but as participants in its unfolding wave function. Our presence, our measurements, even our wonder, are part of the story the universe tells about itself. And as you sit with this thought, let it settle gently. The universe is vast, with histories branching and intertwining, yet it coheres into the world you experience here and now. You do not need to resolve every paradox or master every equation tonight. Just as Hawking sought calm clarity within the complexities of the cosmos, so can you. Let the day's noise recede. Breathe steadily. You are part of a universe that contains its own answers, and in that assurance, you can find rest. Drift into sleep, carried by the quiet certainty that the cosmos holds you within its timeless whole. And so, my friend, we reach the end of Hawking's journey, a story of courage, imagination, and the endless curiosity that drives us to ask what lies beyond. If you're still awake, I invite you to explore another video waiting for you here on the channel, A New Path Through Science and the Stars. But if your eyes are heavy, let them close. May your dreams be gentle, and may the universe itself cradle you in its quiet expanse. Sweet dreams among the stars.